And I have Abhijit and Sreenath and Ramalingeswara. I will call you Ram henceforth. Very tough name. And they are, of course, supported by Subhash. He is sitting somewhere there, who is Adani's corporate communication in charge as well. So he has helped them a lot tremendously. So let's clap for them to start with. The reason is you can look at them, a very young and enthusiastic team. And I really wondered. I was expecting people like Mohan or somebody, to represent Adani and L&T for this prestigious project. But look at them, very young, dynamic, enthusiastic, and still so much responsible. And I was fortunate to go through their presentation before all of you did, and I was sort of zapped. And let us now move over to this team. Would you like to take seats, and one by one we can come over? So this is a presentation. We are all lucky to get a glimpse, the first glimpse of Navi Mumbai Airport. It's going to happen in phases, but they are going to give you a sort of precursor of the things to come there, and the first phase that they are going to present, how it has been designed, implemented, erected, and the status of work as of today. Of course, the Navi Mumbai Airport has been grandly designed by Zaha Hadid, so we can expect fabulous flowing form of the building. And in 2017, this competition for Navi Mumbai Airport design was held, and Zaha Hadid was selected. And in 2019, the final concept came to Adani's. And from 2019 to let's say 2021, end of 2021, they were engaged in finalizing the concepts, nut bolts here and there. And L&T were mobilized. They mobilized somewhere end of 2021 to the site. And in the first half of 2022, they started the detailed design. So this is the journey, 2017 to 2022. It was all planning and design. And since 2022, this is just 2024. Within 2 years, you will see how far they have made this progress. And approximately 10,000 metric tons of steel in the roof structure of the first phase. And I did some other calculations as well. You would ask, why did we wait for 2 years to erect 10,000 metric tons of steel? But the roof comes after you build all the lower structure. And that is almost 1.1 million cubic meters of concrete, requiring 16,000 metric tons of reinforcement. Now that has been constructed so far. And now roof is also there, which now they will tell you the whole story. So now we have here Abhijit Kane from Adani team. He is heading the structural design team from Adani. He will be presenting concept and schematic of the project. And then we have Ram, who will be talking about quality control, construction sequence, material and welding tests and all that, how strictly they are monitoring all this. And then we have Dr. Sreenath from L&T, EDRC, and his team, of course. Predictably, we have Surya Prakash in that team, Bhushan in that team, and Sreenath will be presenting the story of design and detailing. So let us move over to the first presentation, concept and schematic by Abhijit. I will be asking you some questions in between. Is that okay? Fine, you carry on.
Hello everybody. My name is Abhijit Kane. Girish sir told you that. I'll start presenting the concept and schematic at about macro level of the structural scheme that we arrived at before handing it over to L&T for DD and GFC design. So we'll start the presentation. Okay. So this is the final phase of Navi Mumbai Airport. All 4 terminals. Oh, okay. Thank you. This is the final phase of the entire completed airport. You will see terminal number 1, terminal number 2, terminal 3, terminal 4. These are the passenger terminals. This is the cargo terminal. These are the 2 runways and the network of taxiways and aprons. If you see, this total plot area is around 1160 hectares, and GA terminal will have itself 65 parking stands. Then there will be MRO, fuel farm, support facility, utility buildings. It's a complete infrastructure setup. This is the iconic image of, looking at this, you will easily make out that this is done by Zaha Hadid. So all these curves and organic forms. This is the view looking at the terminal from the land side, the departure roadways. This is a 20 million passengers per annum terminal, first phase. Total area of this built up area is 2,25,000 square meters. Footprint is approximately 80,000. It has got almost 2.5 floors, 2.5 floors. The head house roof, which is the processor, which covers about 45,000 square meters. The forecourt, which is the roadways and the curb, that roof covers about 20,000 square meters. The west and east pier, which are for boarding the aircraft, they cover about 14,500 and 5,500 square meters, put together 20,000. Okay, so this is the overall footprint of the terminal. This is the roof plan. You have pier roof, you have processor roof, and you have east pier roof. Processor roof is a complete 3-dimensional complex structural arrangement, framed arrangement, whereas pier roofs is a relatively simple plain frames, modular construction. You can just go on adding the number of bays as you want. And it has got complete modular space frame analysis. It doesn't depend on some specific lateral load resisting systems. Whereas this structure entirely depends on certain lateral load resistance, so it's a fixed system. This is the bare frame view of this terminal. You can see the trusses here, whereas you will have a maze of columns and beams and portals and trusses here. Same with east pier, like west pier. And this is the roof on the forecourt. These are the roadways which come at drop off and go out. So it's just some 3D images. These are the passenger boarding bridges. This is the bare frame picture. It's quite dense because the scale is small and there are so many members. It includes even the tertiary members like skin supporting structure. Okay, now if you look at this roof architecturally has a ridge here with a slope in this direction and this slope in that direction. These are the drains which are planned by the PHE and architects in such a manner that without changing the cross section you achieve the slope, because the whole roof falls down. So this point is a high point and this point is a low point for every drain. So you don't need to change the cross section to change the invert level. The cross section will more or less be remaining same, and then still you achieve the slope to the end. And then there is a garland drain all around. So these drains will drop into a garland drain which takes the water down to this, and this system is designed for 100-year worst rainfall. I will just explain the structural scheme here. As you can see here, this terminal is supported by 17 columns, pods, 4 columns which are drop-down columns, 2 edges which are supported on large service corridors which takes up and down the services, and 2 columns at the end of large cantilevers here but which are literally like pencils. I mean, those columns are very thin columns just to reduce this cantilever length and economize the structure. I'll tell you why that cantilever was not taken as I come to the primary truss description. If you see the column orientation here, this is a peculiar diagrid orientation. We have not taken orthogonal orientation. The advantage is structural engineer gets a economical span to design, so it's a economical structure, and architects get a very wide space to because you know when you enter the terminal your journey is generally uniflow. So architects get the wide spacing of the column visually and functionally, but structural engineer has a very reduced span. So now you can imagine this 51-meter span of truss and 72-meter span for the architects to for the function and aesthetics. Okay, these are 17 columns, these are 4 drop-down columns, these are 2 pin columns, and these are 2 edge trusses which are on this. You can see that, I will show you in the next slide for the arches. These trusses are called Toblerone trusses fondly by Arab designers because they are triangular in shape. If you can see here, 2 top chords and 1 bottom chord. They are infilled by secondary trusses and they are infilled again by some ties. So in all, this whole thing becomes a very rigid diaphragm in its own plane, so the deflections are quite under control because of this action. Okay, so these are the columns coming from the terminal, and these trusses fly over and rest on the arches which are formed by these columns. Now as per Zaha's design, you will never know where the roof ends and where the column starts. It seamlessly turns down into columns. So these 4 arches, 3 arches, seamlessly flow down to the ground as columns to the mother earth to take the load, and they are sort of a valley-shaped columns, finished column. So they take the rainwater also down along the valleys and drop them down to the gutters all around the terminal. And these columns, these trusses, this is the shape of that truss. Now this is that what I called as Toblerone truss here. The purpose behind this shape was we found out in the analysis that most of the time this truss was having downward bending. There was certain upward bending, but the compression created by upward bending reversal of wind was not as significant as the high compression caused by dead and live load and gravity loads in the top chord. So this shape was quite efficient. This section is almost equal to these 2 sections. So you can imagine the type of loading here. Okay, this is that iconic image of the mega column that you will see when the structure is finished. This column is inspired by the lily or lotus as you call it. When you stand here, you will be looking up, looking like as if you are looking at a lotus from below the pond. So that's the shape given by the architect. It's architecturally also efficient because it has got a very small footprint which gives a very large usable area at the ground, and it becomes larger at top where you don't need much area for function. So that's good enough. And structurally also, if you see, this is that form which is inside that. This helps because of the loss of stiffness here is quite sufficiently compensated by a very widening column and a pod here. So this is a very good confluence of architectural and structural engineering, even in the diagrid arrangement as well as in the column geometry. This is a typical panel formed out of 4 pods plus 4 Toblerone trusses interspersed by straight, simple plain trusses and then purlins. These are some of the skylight arrangements here, but that's a secondary structure. Okay, this is that truss. Most of these trusses are made in tubular sections. These are the pods where they meet. This is the slat ceiling arrangement. Now here the false ceiling is not opaque. It's completely permeable. There are metal slats going in twisted profiles. So this slat ceiling, if you stand here, you can see the roof above, if you see between the slats. So these are completely permeable slats. So all the ventilation takes place through the roof, and there are air extraction fans on top of the head of the mega columns. Okay, so this is that, this is the interior. You can see the intricate maze of structure. This is right up to tertiary structure. These are the purlins which are given for suspending the tertiary structure of the slat ceiling, which will be a separate vendor which will supply that. Okay, these are the arches that I was talking about. They just fall seamlessly down to the ground. So these trusses flying from the facade, they fly over this, rest on the arch and then cantilever out. So this arch, this cantilever and this was proportioned in such a manner that the truss behind also got some relief because of the cantilever here, and this arch was not subjected to excessive torsion by its specific inclination. So Daha and Arup and L&T did a lot of work to exactly position this arch in such a manner that it's self-stabilizing. Okay, this is that arch. And these are the massive foundations here. This is the forecourt I was talking about. This is the check-in vestibule. From there, almost 80 meter across, there is no column. This whole thing is supported on freestanding trusses. And those trusses directly fall down on arches, and arches fall down onto the ground for load transfer. This is the maze of structure that will be seen before it gets cladded entirely. Okay. This is another view. So arch number 1, arch number 2 and arch number 3. This is that view which is the bare view. At the perimeter which I showed you on the left and right of the terminal, there are edge trusses which are supporting the left and right edges of the roof. We have certain area which is going much beyond these service cores. So what was done is a huge cantilever bracket taken out from here, on which this circular truss, which is we call bullnose truss, which takes the drain. So this truss sits on this. Otherwise this would have been a very long span and unmanageable, and it would have put huge load on this. So this truss was so proportioned that to a certain extent it releases the load of this curved beam from the main structure. This is the pier roof we are showing. This is the west pier. These are the fixed link bridges to which you will have these rotundas which are mechanical bridges, and these are the facades. Everything is structural steel, as you know. This is the bare frame view. This is, as I told you, is a very simple modular truss construction with ties, bracings and purlins. Nothing, spectacular about it. This is again a very simple, straightforward box girder formed out of triangulated truss on all 4 faces, supported on piers and the ramp house. Just one interesting connection detail here. This is the connection between the facade mullion for the head house, which is inclined in plane, and this has got a substantial cantilever in this direction. So to isolate this cantilever from this in an inclined fashion so that the load of the cantilever doesn't get transferred to this mullion, and mullion is only subjected to the facade load and the wind loads, this double hinge arrangement was developed. So this will allow free movement of this as well as free movement of this, and free movement of this in this direction because of wind load. So this is one interesting detail that I put at the end of this slide. That's about all. I'll just run you through the, I'm sorry. This is the fixed link bridge, and this is its bare view. This is supported, this is on the ramp house, and these are the 2 piers, and there is a small cantilever which connects it to the actual pier from where you board. Okay, just go through this and you can see the present status of construction. This is the latest slide drone shoot. We required about 7,500 metric tons of steel for head house and forecourt. piers required about 1500 metric ton steel, facade required about 1000 ton steel, and the reinforcement consumed here was about 16,000 tons. So this is the present status of construction. Thank you.
That's fantastic, Abhijit, and you narrated it very well. So I would like you to talk something about construction sequence, Ram. Construction sequence. You told me something about that hill being broken and all that. So that was quite interesting. Yeah. That 80,000 square meters of footprint supported by 17 columns. Yeah, but internal 17 columns. So average 4,700 square meters per column. That's the average. It's humongous.
Good evening, everybody. I will take you through the QAQC processes adopted for this head house roof as well as the construction sequencing. In the Navi Mumbai International Airport, whatever all the sub-projects we implement, we follow this process flow chart. These are basically the QAQC processes which are implemented in the various stages of the project. Like after finalization of the specifications, then the source approval will happen for the materials. Then once the materials are approved, then checks will happen on both at the manufacturing units as well as at the incoming material at the site. Prior to start of any activity, method statements and inspection test plans are being finalized. Then we will be having a site mock-ups as well as benchmarks. Benchmark is basically the detailing with that particular member, interaction with other services and other things. So we carry both. Once those are approved, then the installation will happen for all the works. So those are being monitored by the stage inspections. So once the project is completed to the substantial stage, then snagging and desnagging will happen. And then after snagging and desnagging, then the commissioning and decommissioning tests and all those things will happen. And the effective implementation of these overall processes are monitored through the audit process, and as well as the effective implementation and lessons learned will also be monitored through the audit learnings. So coming to the quick glimpse about this roof, the sections used are circular hollow sections, rectangular hollow sections, then square hollow sections, and UV and UC. And here the major erection equipment used are a crane of 1250 ton, a crane of 750 ton, and two cranes of 600 tons and then a 300 ton crane. Why 1250 is required is because of the reach it required with respect to the weight of the particular component to be erected in the center of the roof. And coming to the connection details, basically there are welded connections, butt welds, fillet welds, as well as bolted connections. So coming to the sequence, once the casting of foundation bolts are done, then the column is erected in three segments. First segment and then second segment and three segments. Once the column is erected in three segments, in a particular grade, after erection of all the columns, then main truss is being erected, then a secondary truss, and then they are connected by the ties. And the final photograph is the overall view, how it looks like. So coming to the QAQC testing activities, yes, right from the structural steel samples, those are being tested in the third-party laboratories before being sent for the fabrication. And that is the process followed. And regarding the welds, basically all the tension butt welds are being tested by radiography testing. And other than the tension joints, those are butt welds are being tested by the UT testing. And apart from that one, for fillet welds, LPT testing and MPT are being carried out. So also the DFT checking for the overall paint thickness and paint adhesion tests are being carried out. So this particular site is one of the most challenging site in the infrastructure industry because the terminal is exactly lying on the footprint of a hill. So what we need to do is we have to excavate the hill, and as the hill progresses backwards, the construction will start. That's how it is sequenced. So it is very important that, so there is a scenario where the construction will also happen in the site and excavation will also happen with the controlled blasting. So it is very important to monitor the vibrations and control the vibrations for the structural safety of the RCC elements as well as grouts of the structural steel elements. So how those have been done? The blast designs are optimized. The designs are done in such a way that our vibrations are within the control, and isolation distances are followed. 200-meter isolation distance is followed between the construction as well as the excavation, and isolation holes are adopted between the construction site as well as the excavation site. Those will help in dampening the vibrations. So as per the codal practice, the PPE, we measure the vibrations with respect to peak particle velocity. The PPE allowed is 20 PPE. So month on month basis, those are being monitored. Those are well within that levels. What do we use to monitor that PPB is a seismograph and a geophone. So coming to the another interesting issue is, we will be having, as I said, all the tension joints are to be tested with RT testing. So at peak, Navi Mumbai construction site were having a workman of around 5,000 numbers. For conducting an RT test, you need to evacuate the people. So evacuate the people, then do a test, and if it needs to be reshooted, then again it needs to be evacuated. So that was posing to be quite challenging. So accordingly, we have explored the option of advanced ultrasonic test, which is phased array ultrasonic testing, and we conducted the study on that particular testing methodology. So what we have done is, we have taken the different members, different joints, and we conducted the both type of testing, RT testing and phased array ultrasonic testing. And interestingly, we found that for all the scroll samples of different types what we selected, the results are exactly matching. So subsequently, erection butt joints, we are testing with the PAUT testing.
So these defects were purposely introduced?
There was one sample where defect is introduced, and there is another sample where it was perfect, and other are the regular joints. So simulation and study has been carried out for both the cases, and it is found that the results were exactly matching. Yeah, and also one of the limitation in the earlier ultrasonic testing what we have is, it is left to the operator to analyze. We won't have any documented record. Whereas PAUT has got a recording device wherein you can store the data and we can access at a later date also.
Right.
So these are the comparison reports which was conducted by a third-party expert agency. So these are the merits. And another challenging aspect what we faced at that particular site is, in the erection site, in the peak moment, we used to have a welders of around 60 to 100 numbers, out of which the welder qualification of the welders are different. Like some are qualified for 6G, some are for a different position. So to track exactly the type of welder who is doing that particular joint was quite challenging. When there is a misplacement of ID cards or such kind of things happens. So what we have done is, we have introduced a QR code system wherein that will be pasted on the top of the PPE of that particular welder. So anybody who walks over the site can scan with the mobile, and you will get complete details of the welder and what position he is qualified and whether he is a, those measures have been introduced, and with which the inspection engineers are easy to cross-check the welders deployed.
I think that should be emulated by all of us, the welders qualifications by QR code. It's a very nice idea. That's right. Yeah. And anybody can go and scan.
So yeah, traceability is there, so it will help the system to run. And these are some of the photographs with which the roof has
So
been
this is quite
completely
complete. So you said 90% erection is done, right?
Yeah, roofing has started in some portion and certain portion the members have.
So what is the roofing material?
It's a Kaljip roof. It is a
Okay. Standing seam cal.
standing seam. Yeah, thank you.
Yeah, great, great. That's great. And now we have Dr. Sreenath going to talk about actual design development and implementation, that is erection on the site, fabrication.
Already we had 2 presentations and you got some glimpse of it, the concepts, how it was developed and the quality aspects. I'll just run through the possible extent, whatever the execution design, structural member designs or structural system design, then to the connection designs and some part of execution as well. Yeah. So this is the outline. I'll just briefly, 2 slides, I'll cover the overall plans and dimensions and then structural system and design parameters. Design parameters are very limited to the very unique parameters or rather which is not commonly used. Then claddings and facade, what is the system intended and where we are standing. What was the concept, what we did in DD and what is going to be the final outcome. And especially what we did for internal study and what's implication and what is generally not expected, what all things have come out of that, how we have introduced into that into the designs. Finally, different execution stages briefly I'll be covering. Yeah. So first let's see the overall plans. This we have already seen. We have head house and it has got 2 parts. First part is, this is the head house and from here we have a facade which will be separating the external and internal areas. This is called the forecourt where the arches already we have explained. Then we have east pier which is relatively smaller, 4,500 meter square area and this is 5,500 and this is 14,500 meter square. This is west pier. We have 21 FLBs. From the FLBs, passenger boarding bridges are there, but that's a vendor supply item. So we have designed these systems and I'll be focusing mostly on the structural steel system. Now coming to the dimension, the overall length of the airport is around 925 meters. Within that 300 meter by 150 and another 80 on the forecourt. So this is the dimension of the head house structure and piers 425 meters for the west pier and 225 meters for the east pier. So altogether 925 meters. Let's just have a brief look. Already he explained the concepts, but I'll just run through what is the system we have here. So we have 17 columns. These 3 are mega columns which supports both head house portion and forecourt portion. And these 17 columns will have a varying height which I'll show. These are now tapering columns or we can say which tapers from say for example 1 meter at the bottom to 22 meters on the top. So I'll just go through the dimensions next. Then from connecting the columns which are 50 meters apart, we have triangulated trusses. In cross section it will be triangle, that's also explained. That will form the system. From there we have secondary trusses of varying lengths. Subsequently, we have then ties connecting at regular intervals to break the span and then on connecting between the secondary trusses, purlins are there. On top of purlin, you have a built-up liner sheet insulation system and the top standing seam location, standing seam sheet on the top. So we have a slope towards the south. This is towards the south here from this line and from here it is sloping and this have waviness, but altogether slope is towards the north. There are edge trusses which support a bull nose system. I'll show some section of that, which carries the services, downtake pipes and our catwalk walkways there inside for services. And it's all in a single envelope. And these 2 sides we have earmuff structures. I'll show some cross section of that as well. Now, coming to the system, here you can see that these are cantilever trusses which comes from the primary truss, which support the edge trusses. And as he said, we have 2 small size columns, 550 dia columns, which reduces, make this from a cantilever to a simply supported at this end. These are called transverse, which supports the trusses from secondary trusses on the forecourt side and this system, secondary trusses from here. Now, these arches are also uniquely designed. It has got a torsion or twisted shape along the length itself, which balances actually. We have cantilever overhangs from here. And along the tip of the arch, we have gutters which take the water down. We have two cantilever trusses, 18-meter long. That is 3D cantilever truss. That is also there inside. Yeah. Yeah.
Just to tell you the reason behind that tip column at the edge, two small tip columns at the edges is because we have got triangular trusses. Had we left it as cantilever, the whole triangle would have been inverted because the bottom compression single member would be too large. So that's the reason to maintain the truss shape to the same, we introduced a pin column there to maintain the bottom tension.
Yes, and moreover, the spans are so high that with the dimensions of the truss between these, basically the grid dimension is 50. He has also explained. Your column dimension on the top is 22, which brings down your primary truss effective dimension is, or span is only 32 meters. So this truss is optimally sized for that 32 meters. If I bring in a big cantilever here, the design will go wrong, or rather it will not fit into the conceptual system. So just to show a system, this is the triangulated primary trusses, secondary trusses, ties, edge trusses, all these are just shown. Yeah. Now coming to, these are standard things. 350 grade is mostly, 99% is 350 grade only for small connections, or something we used 250 grade. Mostly IS codes. And coming to the connection design, since we are using Ideastatica and we have to go to the plastic stage, we had to use Eurocode for the limiting plastic strains majorly. Then Stat Connect Advanced is used because the model is so huge, and Ideastatica for most of the connections. And these are the temperature faults based on the study we have got, and that's incorporated. And wind load, we have done a internal study, and based on that we have considered the wind load for the structure as well as the facade system, everything. So that I'll go a little detail in a few slides later. And coming to the seismic, the different thing is normally we'll go for ductile detailing as per section 12. Here the difficulty is, it's a portal system. Portal system is made of column which is a truss as such, or it's an articulated system. Then the beam is again a triangulated truss system. So it's difficult to predict where the plasticity will happen, all that. So we have to go for a rigid system. So NBC has this clause. You can use our R value of 1.5 to design the system as rigid as possible, and then as per the requirement and go that. Then,
Now
in
you
any
said
case,
one.
with such rigid frames, except for probably the base level, there would not be any plastic inch formation.
Correct.
With such a rigid diaphragm action at the top. So it was safe to take it R equal to 1.5 rather than R equal to 3 or 4. And in any case, most of the places wind was governing, so
Yeah.
it didn't really matter.
we have a pin-based idealization as well. Another point is bidirectional, which generally we don't use. We have a concrete system with orthogonal system, rectangular, and this is 45 degree to that. He has already explained. So we have a combined system, which is we cannot put a normal seismic in X and close with that. So we have considered seismic in one direction plus 30% of seismic in another direction. We had complexity in bringing out the forces for connection design though, but we had to do that way for the connection design in Ideastatica. Now we have to use, because of the complexity of the size, the spans, we have gone up to 1100 by 60 thick. And in the previous panel discussion, it was discussed, we had to import, it's not pride, but unfortunately we do not have. I think many of our manufacturers are now coming up with bigger sections. We have gone up to 60 thick. So here also just rolled and brought it from there. Many of the other sections below 25, 20, 16 and all we got from India, whatever different vendors. Now, this is a structural steel model, just to get a glimpse. All the supports are pin supports you can see, and these are those pencil columns what we are talking about. Next. Now, as I said, from the interface region or the facade which separates the head house and forecourt, it slopes down. So we can see the column height varies from 21 meters to approximate 21 to 14.6. The configuration remains the same. And this single column weighs around 125 tons. So these images somehow, because of the screen size, it's little not clear. We have, see in the initial design, it's just point-to-point connection when you do the connection, structural design. But when it goes to the connections, it's complex. It is time-taking to bring that all profile cuts, and matching it's very difficult. Matching the profile, it's very difficult at execution. So we have proposed connections made of plates, box nodes, or of different shapes, depending on number of elements. Here you can see that here we have only 2 plus 3, 5 members connecting. From 1 member it goes to 5. From that 5 it goes to here, it will have more numbers. So we have up to 13 member connection. So I'll come to the connections later. This is a typical primary truss. We can see that at these nodes we have bigger diameters and bigger thicknesses to accommodate the trusses at that location or strains to be within the limit. Now, secondary trusses are plain trusses, pinned, you can see. And this is the cantilever truss. And this was also a critical design because this has got almost 2.5 meters embedment into the concrete. Because it's 18 meters span, it is supporting the roof structure there. Now, this is the forecourt portion. Beyond, this is the transverse truss. You have an facade system comes here. Now, already we have 3 arches here. I'll go to that. Yeah, these are arch truss 1, 2, and 3. The spans goes up to 112 meters. And secondary trusses are at every 9 meters, which is the standard we have used in this project. Now, the heights of these trusses also varies 22, 21, and I've shown only 2 numbers. This is the largest truss. This erection is yet to happen. Whatever the done part is the head house portion. Excuse me. Now, coming the kind of base idealization is pinned, but even then it is designed for some minimum eccentricity and bolts are provided. 4, we have provided shear key. So there is a shear key below which takes care of the shear. Majorly it's shear only, as per the output it's only shear. But we put the shear key and then we are designing anchor bolts for some moment. So you can see different connection configurations or box knots which is used to connect multiple number of elements joining at that. These are the plastic stresses which goes up to theoretical value, code given value 350 by 1.1, which that is 318. And plastic strains is maximum is limited to 5%. Now these are some other, we can see the number of elements connecting because of this geometry, the number of sections joining we have to use. We have multiple stiffeners, ensuring that we are not depending on the plate bending. We have a stiffened system available there. This is again coming to the primary truss interface or column just goes and receive the primary truss. So we have different flange connections, welded and bolted connections, different types of connections are used for this. Now I'll just briefly go into the cladding in facade. You can see this is the intent. We have our structural steel is here, but the cladding joins the facade but a bigger distance. So this is the concept design stage. From there, you can see both the directions. You have 2 sections with a slope in direction, and this is east-west direction without any slope. Now we have done the detailed design with the connections incorporated. We have a secondary framing made around the structure. From there, vendor will have, the cladding vendor will have a separate system. They'll attach to this system. So this is how, this is the level we have reached up to now. The vendor has to do the subsequent attachment and bring it to this shape. Finally, we'll be having this. Yeah. Now these are varying heights. I'll just run through different heights of facade mullions we have because of the shape and interface with the column. So these are the 3 mega columns. I said the head house and forecourt, it's combinedly supports. And here you can see that the mullions are not rectangular. We have a tapered section which is used for the mullions. And this is column cladding, front side column cladding, which will have a outward projection which starts from the lower level. This is the departure level. So it's a combined system is there for both the columns from bottom to the top. Head house south side, which is the air side of the structure, air side of the airport, we have a slanting mullion where the connection detail, all facade connection detail, he has shown a detail wherein you will not transfer any vertical load or movement to the facade mullions. This is also same. Yeah, this is what I was saying. You have a catwalk. This is the concept design stage details where you have some catwalks, pipes, everything is running there. You can understand, you can see the complexity of the systems there with not many pipes. It's designed for 100-year rain, and over that some additional 2 times cushion. Some cushion is there because there should not be any problem whatever rain happens. So we have up to 700 dia pipe, multiple 6 pipes are there coming from different gutters on rooftop.
For 100 years worst rainfall and 2 times the redundancy.
So every drain has got 2 pipes, one backup like that. Now coming to the wind tunnel study. Yeah. So this is the terminal which we were showing, the head house, forecourt and piers and all with the approach road. And so this is the first model we have. But you can see that the independent of whatever the wind force we get from this will get altered when you are going to have the next set of, this is the close-up view of the model. We have multiple sensors in that. I'm not getting into the details of that. We are getting input from them for the different transducer location. They will process and give the data, wind tunnel data. Now, when it comes to the second phase and third phase, you're going to have a system. So there will be an interference of wind acting on structure, other structures on this. So that part is also taken care in the current design itself. Obviously, it should be done. We have taken care of that, and that incorporated values or design wind pressure values are considered for the design. Now, That wind pressure values we have taken into grid sizes, and this is one just case I'm just showing. And unlike, you don't, as per the code, if you go for a almost like 5-degree slope or 2.5-degree slope, you don't expect a wind load downward. But in this case, we are given with a wind load downward, which is not a conventional way. We had a 50 kg, roughly 50 kg downward load all over the roof as a acting on dead, live, plus everything.
Despite less than 10-degree slope.
Yeah, it's 5% slope only it is there. And all the different cases. And we have all so many segments because of the shape, so many segments the wind tunnel data is given. So this is also for the forecourt portion. So this is how it is processed and all given in detail. I'll just rush through. So even for the facade portions, different region, this is a bullnose portion. So all these regions, even for the claddings, different segments, they have given the wind tunnel data accordingly. In the design, it's considered. It was a laborious exercise to bring that into the design model. Now I'll just show a few snaps of the design stage. Now you can see the first column we erected, we brought in as first segment only up to the level 1, or level 1 means level 1 of the column. This is, so we have the pit ready for the with the anchor bolts ready there, and this exactly came and sat with the perfect positioning. And subsequently we came to a stage where, this is another position. Subsequently we went through the legs, 2 levels, together we brought and erected. And in the final stage we have brought 124-ton mega column in a single erection also it's done towards the, as we progress in the erection part. So this is one column erected. We had trestles supported until the primary trusses are connected and it is stabilized as a 4-system part. This is one primary truss erection you can see. You can see the primary truss connected. As I said, the dimension from here to here is 50, but it brings down to, brought down to 32.
So how many splices are there?
No, 2 splices here is there, and for the transportation, that's a good question, because we have 32-meter span, and we have used 16-meter trailers, so we could bring it in 2 segments and join it together.
How far is the workshop?
90 kilometers, Wada, I think, sir, it's in Wada. Sorry, highest piece lifted. Transported or lifting was 124 tons. 124 tons single lift we did. This is one primary truss grid system is already installed. 4 numbers is erected there. This is some more portion of the structure installed or erected at site. You can see the ties, connecting ties, top chord level and bottom chord level ties are there. Few purlins are placed. We have, in fact, the bottom side, as he has shown, we have on top purlins, and bottom side we have false ceiling supporting members at every 1.2 meters. Now this is the now you can see the liner sheet is put over some of the places, and this is the south side. So for head house, that up to the transverse truss region is what we have done. Forecourt portion is in the progress. Fabrication and direction assembly process is in progress. This is how massive you can see from, because of the slope you can see that it's all from top level. You can see that there's a bigger thickness because of the slope of the structure, roof structure there. This is the pier structure. I did not go in detail. This is regular structures only. This is 35 meter wide and this is 22.5 meter wide. Each pier is smaller relatively. And both side 5.5 meters cantilever system is there, and partially facade mullions are also erected in here. Yeah, this is the overall progress, both west pier and east pier. That's it. Thank you all.
That's great. So I think this is the first glimpse of the project, and I'm sure there will be many more presentations when more and more aspects of the project will be revealed. I believe for next 3 years, we'll be inviting them again and again for getting more information on the project. Thank you. Thank you. Abhijit, Sreenath, and Ram, and Subhash for compiling a wonderful presentation, the first glimpse. Yeah, yep.
This project is very close to our heart. We have worked from 2017 on this project. And it's a tandem work with value addition, value engineering, many things, change of guard from GVK to Adani. There are many ups and downs. And my team of Bhushan and Sreenath, we did wonderful job with respect to continuously working and value add and doing this marvel project. I think we are passionately attached to this project. That's our thank you. Thanks a lot.
Yeah, that shows. Okay, any questions? The panel is here.
The basic form of the building, mainly the envelope, was completely evolved by Zaha Hadid. I mean, Zaha Hadid and Arup's design, I don't think we changed something that changed the basic geometry of the form. It is, we are stuck to the basic geometry. Maybe some tweaking inside to adjust the structure. I think KSP wants to say something about this.
Zaha Hadid's concept was much more complicated, to be precise. We did modify the roof for the forecourt we retained. The beyond was also having complete curvature. Since it's a very functional and the appearance wise it will be the same even if you keep the forecourt as the same curvature. Balance being a functional part of it, nobody will see even if it is visible from the outside. So we did make it as a completely sloped instead of so many curves on the roof. But retaining the complete architecture visuality as well as the interspace with respect to the land side and the air side, we could retain the complete forecourt as the curvature. That's the complication of it. Balance is, though it is sloped, it retains the architecture of Zaha Hadid from inside and the forecourt side. The feel is same.
So finished form is sacrosanct.
Yeah, there. Dhananjay.
I think it's a huge structure and there must have been number of structural alternatives, proposals, theories to get to the practical point. Has Arup tapped any continuous shell proposal for this complex form which is now coming down like inverted trees at 17 locations and having been followed a shell form? Was there any option tapped during
You mean
conception?
in RCC? Shell in RCC?
Yeah. Or composite grid shell.
No, Arup never explored that form. It was, finally it's about constructability also. So probably they thought steel encased or cladded with finishing is the best option to go.
Right. So right from the beginning, this was conceived as a frame structure.
Yeah, and see that lotus bud concept with so much of complex petal form merging with the slat ceiling, that was sacrosanct. So now if you try to go to, if you see the ceiling, it's not a continuous shell. It's a completely perforated ceiling. Only the lotus buds are opaque. Everything else you can see up and you can see the trusses and purlins also. So the form was slat ceiling, which was only possible in structural steel.
Yeah, okay, yeah.
No, and
We can discuss deeper.
the form is so complex that if you try to do it in some kind of concrete shell or something, interpreting the analysis results as regards stresses and all that would have been very difficult. This structure is meant to be in structural steel, where you resolve all the forces in linear members and it's very easy to interpret those results, design the members. So this is a perfect example of why structural steel for a particular, form. So I think there was no other option.
Yeah, I mean, we can see that it is very constructible steel, fast,
That's right.
and fast enough, although complex, yeah.
That's right.
I know where it is coming from, yeah.
If you see the span on the forecourt, that's about 78 meters, right? 80 meters. 80 meters. So constructing anything of that magnitude in RCC or composite would have been extremely time consuming. You think of the shuttering, that form has really real organic geometry.
I mean,
You can ask,
absolutely.
Sreenath.
Instead of designing the formwork for that span, I would rather design the structural steel for the roof and get it done.
Sacrificial formwork can be a solution. Sacrificial complex formwork
Yeah,
can
but
be a solution.
you need props and staging and
formwork
all that.
Okay, okay. Okay.
Anyone? Yeah, here.
More bolted joints that could have probably made things easier, less welding at site when you're lifting things, welding them up at 20 meters. And then of course, testing of each welded joint becomes that much more complicated. Whereas you can have a joint designed and prefabricated on the ground, a bolted joint, you lift the member and bolt it together with, face plates. Did you think of that? Because I didn't see too many of the bolted joints. I was curious about that.
True. Basically, we have tried to avoid maximum of welding in position. So whatever the welding, as I said, towards the end we came, or rather progressively we came to the column totally fabricated down and then lifted it and kept it there. Now, coming to the bolted joints, we have used flange connections at the possible extents. Yeah, bolted systems are used for flange to flange connections to the extent possible we have. As I said, now coming to the PTs, if it's a 32 meters, we have only single joint that is made at that location with the bolt welded at the site, at the ground. It's a fabrication yard and taken it up. Yes,
Yeah,
obviously
so
there is.
that's exactly the question. I mean, instead of that welding joint there, when you're joining two 16-meter pieces, making it 32, could you go for a bolted joint there? It makes it much quicker, I believe.
No, we have bolted splices at 16 meters. We have certain locations we could not, because certain locations the clearance was also less, and then we have the complexity of joint exactly aligning and getting bolted. You have to have a perfect fit there. So few shift itself was creating. That's a practical constraint. Unfortunately, we have to admit that it's few off. It's not possible to do that. So there was a lot of resistance, and we came to a balance. Okay, these joints we will do in bolted, and these in welding. That's a
In other words, welding was a solution to the problem of
Matching
Matching,
the joints.
See, if you see a few joints, there are joints with a minimum of 6 members meeting or maximum of 14 members meeting. Such a joint, making a bolted connection is physically impossible to make that geometry, because if you see the joint, it's a huge box where all the members from all directions come and get welded. There, if you go for bolted joint, the joint itself would have been very big to have a space for bolting and accessing the bolt for tightening, etc. And then you will require probably high strength grip bolts only.
Thank you.
Because your section size is very big, 1100.
That's at the base, of course. 1100 is at the base, but even at higher level, we have got 500 and 600 in the column.
I think audience is stunned. No more questions. Okay, so we call it a day. Anything? Anyone? Yeah, please. Wait for the mic.
So at the column nodes where many elements are getting connected, how the testing was done over there? Column nodes.
Column nodes actually are done at the fabrication yard only.
Okay.
And there are criteria is like this. All the butt welds, there are two types of welds. Basically you see in these elements. One is butt weld and the second one is a fillet weld. All the fillet welds, those are being tested by LPT or an MPT. Butt welds, those are tested by RT. Tension butt welds are tested by the radiographic testing. And apart from tension joints, it is with UT. Yeah. PUT is subsequently, yeah. Now, those particular column element, it is done in the fabrication yard itself. And all which are converging into that particular node, those are fillet joints. Those are not the bed joints.
All are fillet joints.
Yeah.
And most complicated joints are in shop.
Correct.
All boxes with the number of pieces. See, all boxes with the number of pieces, it's made at the factory and brought to the, site for the execution, because those are very complex and you can't do it in the site. As I said, maximum 13 or 14 member connecting box nodes are there. It's too complex and to get to that shape and ensuring that quality there.
Yeah, correct. It is done in the fabrication.
Yes, please, sir.
Thank you.
Yeah, here.
Yes, sir, please.
Hello. Yeah, on the roof system, I could see triangular trusses on the grid lines.
Yes, primary trusses.
And you had secondary trusses, not normal to the main triangular trusses, but at 45 degrees, you are connecting it.
Yes, sir.
Why was it like that? Why was not normal to the triangular truss? Was there any specific reason for that?
Yeah, basically, see, you have the top sheeting system, sir. Then you have purlins perpendicular to the sheeting direction. Then purlin sits perpendicular to the secondary trusses. And we have all the secondary trusses except for the periphery. The roof slope is towards the south.
Okay.
So that indirectly tells us we need the trusses
to run
also
the
in
purlins normal to your trusses,
Yes.
secondary trusses.
Yes.
Okay, thank you.
So the column and the primary truss grid was in diagonal form. The purlins and secondary truss had to be in north, south, east, west. So there was no other choice.
Done? Okay, so that's great. So see you next time again and give us some more information next year. Thank you very much. Thanks.